some momentum here. So look on page 277. I talked a little bit about yesterday about momentum. I sort of defined it for you. Let's have a look and see what this textbook says. Many people have a vague idea of what momentum is. It's often associated with a change in the flow of support for a candidate in an election, or maybe a sports team gaining advantage by changing the flow of action and pace in the game, or starting a fight. They always talk about the hockey guys, right? Start a fight to change the momentum. The idea of momentum contains some notion of a change in motion. Momentum is some change in motion. Does there have to be a change in motion for there to be a momentum? Can an object have momentum without moving?
Yes. No, it can't.
Like an iPad sitting there, or a deck of cards sitting there on the table. Do they have momentum? No. There has to be motion. There has to be motion. There has to be motion for there to be momentum. Does that iPad or deck of cards sitting there have inertia? Yes. Okay, so don't people get those confused a little bit.
Definition of inertia.
Inertia, okay. Inertia is an object's tendency to stay at rest or in motion. Right? Objects tend to keep on doing what they're doing. So it says there in the kind of the purple orange box, it's not purple, pink. Momentum of an object is changed when an unbalanced force is applied over a given period of time. The resulting change occurs in the direction of the force. The physics definition of momentum is mass times velocity, or P equals mv. P equals m times v. P standing for momentum, because m is taken. The next letter is N. That's for newtons. O looks like a 0, so they have a P.
Are those both capitals?
They're usually lowercase, Mike. Did anyone Google up why P is used for momentum? There was a. Did you try? I've searched a few times too, and I haven't had a lot of success.
That's probably why.
It could be. It's old, like it's been around forever. I think it's got something to do with the word momentum in another language, kind of thing, or.
Oh, maybe like Latin.
Yeah.
Greek and Latin.
Yeah.
Words were related to one.
Yeah, it really wasn't definitive, from what I remember. Okay, so example 1, calculate the momentum of a 1 kilogram duck moving at 28 meters per second. This is a new Biotech Super Performance duck, with wheels apparently, and of a sumo wrestler with mass 200 kilograms moving slowly at 0.5 kilometers an hour, as shown in figure 8.2, right? So momentum is really simple, right? It's just P equals mv. So if you've got a duck, right, mass of 1, he's traveling at 28. What would be the units for momentum? Like mass is measured in what? Kilograms, and momentum is measured in meters per second. So this is 28 kilogram meters per second. Now you would think, right, like 1 Newton is a kilogram meter per second squared. That's equivalent to 1 Newton, because it's easier to say Newton than kilogram meter per second squared. So you would think there would be some guy they could come up with that would have a unit named after him for kilogram meters per second, but you would be wrong. There is no special unit for momentum. Kind of disappointing, really. There's got to be some scientist that deserves it, don't you think?
What do you mean?
It's just 28.
Why did I erase it?
Well, you have to erase it, right? Because there's no units. Is what you're saying?
Like there's no.
No, I'm saying the actual units are kilogram meters per second. There is no special, it's not called 28 Bennett's or 28 Leckies or whatever, right? Like it's kilogram meters per second.
So it is now.
So we write that in.
Yeah.
After.
You write kilogram meters per second after things for momentum. That's
It
the
sounds
unit.
like something like electric. It's like
Yeah, it actually does.
What, Leckies?
Like 24 Leckies.
Ooh,
4 kilowatts. And
you got to watch out for that.
5 Leckies.
They'll get you. They'll get you every time.
Yeah. It's not the Leckies that'll kill you, it's the voltage.
It's
I don't know what that
having to
means.
listen to them.
Okay, so if you got the sumo guy,
Wait, what is that red there?
Is that?
oh, I'm saying 1 Newton is kilogram meter per second squared, but there's nothing like.
Do you need that dot right? Kilogram?
No, it's sometimes you see it in books. The dot means multiply. Like it's not kilogram per meters per second. It's kilogram meters per second. It's kilograms times meters per second. They should really come up with a unit, like really.
Yeah, that makes sense.
Yeah. So the sumo guy, he's traveling at 0.5 kilometers an hour. So you actually have to divide by 3.6 to get it into the proper units of kilogram meters per second. He's traveling at 27.8. Oh, sorry. He has a momentum of 27.8. Okay? So you'll notice that their momentums are practically equivalent, even though the duck only weighs a kilogram and the sumo dude is 200 kilograms. But the duck's traveling a whole lot faster.
What is the point of knowing an object's momentum? What does that get you? You can figure out, like, what is force.
You can figure out how much force. Like, by itself, it's not really a whole lot of good.
Oh, okay, so
Yeah.
it's like another piece to.
Yeah, that's what's coming next, actually. Right? If you flip the page over, when someone asks you whether you'd rather be hit by a piece of chalk or tackled by a serious football player, at first the answer seems to be the chalk. But if the chalk were moving at 250 meters per second, then you're basically dealing with a bullet, and you'd rather be tackled by a football guy.
250 meters per second.
Yeah. Momentum is an important concept when considering impacts, collisions, and how objects in general interact. It's not just an object's mass that's important, but it's the product of the mass times velocity. There's a couple quick questions there that I really don't think you guys need to do. Let's go straight to 8.2. Momentum and Newton's second law. Now you might remember yesterday I gave you a formula, and you said, did you just derive it? And I said, well, not really, but now I'm going to. It's probably the simplest form of derivation you're ever going to see. Okay? Acceleration is delta V over delta T, right? And we know Newton's second law, which says F equals ma. So I'm going to take this A and that A, and I'm going to put them together, right? I'm going to put this in there for A and get F equals m delta V over delta T. Okay?
Why is it T?
Huh?
Why is it mass times
Oh, okay. Sorry, Mike. Yeah, fair enough. You want me to do this?
like, does it matter? 'Cause
No, it doesn't.
delta
But
V-
this is what concerns you, right?
Yeah, that's,
Yeah. Does it matter? Whether it's mass times, like what we're really doing here is we're taking delta V divided by T and then multiplying by M. Or can I just go M times V and then divide by T?
That's actually really simple.
It's all the same thing, right? Okay, so now people realize, okay, this is equal to, if M delta V, that looks an awful lot like
Is that important? That's probably an important thing, huh?
M times V, yeah? So M delta V here is equal to what we say change in momentum. The M times the delta V is the change in the momentum. So we would like to sort of isolate that a little bit. And so what we do is we take that delta T to the other side, and we get F delta T is equal to M delta V. And that is known as the impulse
That was the thing on the board yesterday.
momentum equation, exactly.
Yes.
force times change in time equals mass times change in
Change in velocity.
You're gonna add your-
The left-hand side, the F delta T part, is referred to as the impulse, and this part is the change in momentum part. And the letter we use for impulse is J.
Wait.
Yeah.
Because I looks like a 1 or an L.
I is used for current in electrical terms.
And G is the
J's
next
are-
letter.
I guess. I don't know why they use J.
Because it's the next letter.
I guess.
It's just like they don't use M for momentum, it's on an N and L.
I guess. I don't know why.
Some
Yeah.
people-
Now,
I-
impulse momentum equation is kind of long and hard to say, so I like to refer to this. The F and the delta T, kind of, if you sort of squint a little bit, kind of looks like a word,
that.
fat. But if you're going to say that triangle delta is going to be an A, then this is known as, in my, only my terms, this is known as the fat equals mav equation.
That's
That.
it.
The fat nav equation. Not pH kind of fat either. F kind of fat. Actual fat nav. That's like when I went to Greece and we saw the genuine fake watches. Okay, so fat equals mass. Fat delta T, the force multiplied by the time, is called the impulse. J of the force, is equal to the change in momentum of the object. The equation for Newton's second law can be written as F equals ma, or F delta T is equal to delta mv, or J. Blah, 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 blah. Oh, by the way, what do you think? Okay, so what would be the units for the MAV part, the delta V? I'll put that in,
Kilograms.
I'll put it in green so that, okay? The units here are going to be,
Kilogram.
I said green, didn't I?
You did.
Oh, kilogram meters per second. F delta T, the impulse, is measured in Newton seconds. Newton seconds is the impulse. Okay, so if you flip straight to example 2,
Wait, so what did you say, oh, the nav part?
the MAV part is measured in kilogram meters per second. And the impulse part is measured in Newton seconds. So now this comes into play. We saw the other day when I had the big long blow dart kind of thing, right? But it also comes into play like if you're a hockey player or a baseball player or a tennis player, or basically any kind of sport where you're hitting a ball. Or, well, not throwing, not as much, but certainly hitting, right? When you golf, they tell you to do what when you hit the ball? Follow through.
I was reading about that.
Same thing with tennis, right? You follow through. Baseball, you follow through. Why do you follow through? Even kicking football.
What about basketball? You follow through there.
Yeah,
But I don't actually know.
for
why.
slightly different reasons in basketball, right? But when you're hitting a baseball, you follow through. When you follow through, the ball tends to do what? The bat tends to remain in contact with the ball. And if that ball is in contact with the bat for a longer time,
Physics and stuff!
right? So if you make your time longer, the ball has the same mass, and so the only option is the velocity is greater, which means it goes
It
farther.
goes faster.
If you follow through, it goes faster, right? You know that from playing golf, right? If you follow through, it goes faster.
Ask me if I do it.
Did you know that?
Okay. Do I need to give you an example there, do you think? Like a numerical example?
Yeah, do a little example.
Okay, example 2, a golfer hits a ball of mass 45 grams, causing it to leave the tee at 40 meters per second. Find the impulse imparted by the club to the ball and the change in momentum of the ball. This is top of page 280. So we've got a 45-gram ball, and the velocity of the ball is 40 meters per second.
Should I change? Should we change it to
Yes, it must be in kilograms.
That's why slap shots go faster than wrist shots.
Exactly. Well, and you're hitting it harder, right?
Yeah, and you're in contact with the ball.
Yeah.
Well,
I think wrist shots.
But if you're gonna shoot a wrist shot, right? Like if you just sort of went like that, it doesn't, right? You do what? You follow through. Everything you can think of as an athlete, if you follow through, you're going to increase that time and it's going to go farther. And that's why the marker went so far the other day. Because I increased the length of the tube, right? So here, we're going to find the impulse. Now, to find the impulse, I need force and time, and I have neither of those, right? But I know that the impulse is equal to the m delta v, right, as well. So the mass is 0.045. The change in velocity is from 0 to 40. So it's 40.
Wait,
So,
M delta V equals the impulse?
well, no, maybe shouldn't write it just like that, right? Maybe I should write it like this. J equals F delta T, which is equal to m delta V. Right?
F is,
It just means F delta T is J.
yeah, so F is just the force
5, is that?
Yes. Oh, it's the 5 force, right? So the impulse is also equal to the change in momentum. If the change in momentum is 1.8 kilogram meters per second, sorry, not per, yeah, kilogram meters per second, then that means, therefore, that the impulse, the J, is 1.8 Newton seconds.
Oh.
It's the same.
It's the same numerical value,
Okay.
right? And they do mean the same thing, right? It's just sort of two names for the same thing, really. Okay. If you look at example 3 there, the parachutist on the next page, page 282, parachutist lands, flexes her knees, and rolls in order to stop. Calculate the impact force on a 70 kilogram parachutist falling at 10 meters per second if the time to stop is 0.8 seconds. Compare the force of impact if a soldier lands in a rigid position standing at attention. The time of stopping is 0.05. Like when you jump from a high spot and you jump down, what do? You bend your knees. If you don't, what's going to happen? You're going to blow your knees, right? You're increasing the time, exactly.
He jumped up bleachers straight leg.
Who did?
He jumped up bleachers with straight legs and good time.
Yeah? How'd that go for him?
Knees, but he didn't enjoy it.
As much as everyone else did.
Yeah.
Yeah.
Probably hurt. It's pretty bad.
Okay, so we've got, we're trying to find the force of impact, right? So F delta T is equal to M delta V. It's a parachutist, it's 70 kilograms. The change in velocity goes from 10 to 0, and the time it takes is 0.8, right?
10 to 0? So it's
Well, she's falling at 10 meters per second. When she lands on the ground, she's going to end up going 0, right? The force of the ground on her is going to stop her from going 10 to stop, right? So the force on her is 70 times 10 all over 0.8, which is,
But why is it a minus 10?
it's not. Well, in the book, is it minus 10?
No, I'm asking you why it's minus
It's because it's the final velocity is 0, right? The initial velocity is 10, the final is 0, so the delta V technically is 0 minus 10. So yeah, this is minus, the force is negative. It just means that there's a negative force applied to this person. 875 Newton, that's quite a bit.
It's like 875 apples.
Hitting you, exactly.
At once.
Now, if you're the stupid soldier that's got your knees unbuckled, and the time is 0.05, and you still weigh 70 and you're still 10, right? The force on you is going to be like 14,000 newtons. How do you like them apples? Not so much. Okay, blah, blah, blah. Let's go on to force versus time graphs, and then I'll get to see that.
You don't need both.
So like,